two very important functions. We're going to start with the exponential function. And then we'll continue with the other one. Exponential function. Why do you think this function is called exponential? Just a wild guess. It has an exponent, of course. The variable is the exponent, actually. The variable is the exponent. Before I explain or I show you how it looks and how it's written, I want to ask you a couple of questions. Can I raise 0 to the third power? Can I raise -1 to the fifth power? Can I raise 1 to the 10th power? And can I raise -3 to the second power? So 0 to the third is perfect. -1 to the fifth. 1 to the 10th power. And -3 squared. Good. However, these are not allowed in an exponential function. I cannot have the base of 0, a base of a negative number, base of 1, or a negative number again. So, the exponential function looks like this. A base that is not the variable, it's a number, it's a, lowercase a, raised to x. So there are two possibilities here. A can be between 0 and 1, as you notice, not 0, not 1. Or A can be in the interval 1, infinity. We like to write this, of course, as 0 less than A less than 1. This is the mathematical way of writing it. Or A greater than 1. So as you notice, one more time, 0 is not accepted as the base. A negative number is not accepted as the base. And 1 is not allowed as the base. And now you're probably asking yourselves why. The answer is the inverse function will not exist. That's the only reason. Its inverse function will not exist. Okay? Very good. So let's look at this function, graph it, have an example of each type, and then I'll show you what we can do with this function, transformations, of course, and then it has so many applications. Ready? Okay. So please give me an example of an exponential function with a base greater than 1. Okay, 4, but that's not an exponential function. That's not an exponential function. It's missing something. Exactly. So this is an exponential function with a base greater than 1. Perfect. It's a pure exponential function. It doesn't have any transformations. There are no shifts, nothing up and down, nothing left and right, right? It's just plain 4 to the x. Ready? Good. So let's start with a chart that will give us ordered pairs that we need to plot. And let's see what we come up with. Now, these restrictions that we talked about were on the base. Now I'm asking you, what do you think is the domain of this function? Is this function a friendly function or not? Let's think. Can I raise 4 to 0? Can I raise 4 to a positive number? Can I raise 4 to -2? It's 1 over 16. So what is the domain of this function then? All real numbers. We plugged in everything, right? We plugged in positive for x, we plugged in 0, we plugged in negative, everything works. Perfect. So now let's pick some values. Let's say -2, -1, 0, 1, and 2. Let's plug in f of x, let's plug in -2, and let's see what we come up with again. One over. Perfect. Let's plug in -1. Perfect. Let's plug in 0. Let's plug in 1. Yes, let's plug in 2. Very good. So now let's see, where am I going this way and where am I going this way? If you remember, in both rational functions and polynomial functions, we were interested in determining the end behavior, right? For polynomials, it was like this. For an even degree with a positive leading coefficient, it was like this, if the leading coefficient was negative. For a rational function, so on and so forth. So this time, we're just looking at those numbers. We're not really doing or determining the end behavior like this for other functions, right? But for this one, yes. So let's analyze, where am I going this way? 4 to the third, 4 to the fourth, 4 to the 10th, 4 to the 50th, 4 to 100. Where am I going? Indeed. Now I would like to go this way to see what is the end behavior at the other end. 1 over 4 is 0.25. 1 over 16 is 0.25 divided by 4. 1 over 32, tiny. 1 over 64, smaller. 1 over 128, smaller. Closer and closer to? Exactly. Exactly. So when we say about a function that when x approaches -infinity, the function values approach 0, what does that mean? Horizontal? Yes, but this time only at -infinity. So y equals 0, horizontal asymptote only at -infinity. We have not seen something like this before. The function either had a slant or had a horizontal asymptote at both sides, right? We have not seen a horizontal asymptote only on one side. Nope, you'll see in a moment. So let's graph this function now. The first ordered pair from left to right, what will I graph? Or I should say, what should I plot? Yes, I'm going to say it's this. Very difficult to plot. -1, 1/4. Bigger. Next one. Correct. Next one. I can't. I will go on to the next page. So here's the graph. It does not touch the x-axis. It appears in my graph that it really does. I'm sorry about that. So this is the graph of 4 to the x. I would like us to establish that the function 4 to the x is defined on all real numbers, and I would like someone to give us the range. Exactly, 0 to infinity. This function has a lot of properties. Is it increasing? Yes. So if I have x1 less than x2, f of x1 would be less than f of x2. Good. Is it 1-to-1? By the horizontal line test, it's 1-to-1. Does it have an inverse function? Because it's 1-to-1. If it's any function that is 1-to-1, will have an inverse function. I don't know anything about the inverse function, but can I graph it? Although I know nothing about it. Yes, with respect to? With respect to? With respect to? Exactly. Because I reverse the ordered pairs. What if we just do this? I want you to give me a few ordered pairs that I should plot. to graph the inverse? Yes. So you're going to give me 1/16 comma -2, right? That's what you're going to give me, 1/16 comma -2. It has, these 2 points have to be opposite. So I'm too far down, but that's okay. Okay, give me the next ordered pair. Exactly. So these two have to be opposites. I mean, reversed and not opposites. Okay, the next one. Exactly. The next one. Very good. So here's the graph of the inverse function. It has to be a mirror image with respect to y equals x, because we are reversing the coordinates. So this is the inverse of 4 to the x. I'm not going to name it just yet. We will. So now, this function inverse, f inverse, can you please give me the domain and range? Exactly. That's all I want you to say. So from these two functions, which one is friendly and which one is not? And I have to be very careful with it.
The friendly one is the normal one, because it's how the inverse of vertical asymptote.
Yes. Not just that it has a vertical asymptote, but it has a domain that is not all real numbers. So this function is friendly. This one is not. Can you mention give us two other functions that have a domain that I have to be very careful about, not defined everywhere, that we studied already? Yes, rational functions. They have asymptotes. Okay, another one. Tangent. Tangent, secant, cosecant. Those are functions that have vertical asymptotes. Another one. Square root. Right? No asymptotes, but the square root is not defined everywhere. Right? Or any even root is not defined everywhere. So this function, the inverse of the exponential, will join that list of functions that are not what I like to call friendly. I have to worry about their domain. Okay? Perfect. So this function is increasing on all its domain, so is its inverse. 1 to 1, so is its inverse. Because this is the inverse of this and this is the inverse of that. Okay. Now let's graph it. So y equals clear and 4 caret x and enter. Zoom, I want 6. Here it is. And no, this is incorrect, and we know that. They don't overlap. The blue function does not touch. Eventually, maybe, but it does not touch the x-axis. So be careful with the graphs. Okay? Perfect. So now let's look at the other shape. Please give me an exponential function with a base between 0 and 1. Okay, let's do 1/2 this time.
Mine doesn't like keep on, just stops right there.
Yeah, the software shows because there are different colors.
Yeah.
Yes, but on the graphing calculator, it's, yeah. Okay. Domain. So now remember, we have to add these functions to the list of functions that we know. Yes, indeed, the domain is all real numbers. Same points, same x values. So please plug in -2 and tell me what you get. So hold on. 1/2 raised to -2. I have to flip. So it's 4. 1/2 raised to -1. So in parentheses, 1 divided by 2
Oh, maybe.
So 1/2 raised to -1. Good. 1/2 raised to 0. 1/2 raised to 1. 1/2 raised to 2. So now the end behavior. So let's see where we're going this way. 1, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/0. So y equals 0, horizontal asymptote at infinity only. Let's say this one on this side. 2, 4, 8, 16, 32, 64, 128. Where am I going? Infinity, correct? Okay, so let's graph. So from left to right, -2, 4, -1, 2. Is this okay so far? 0, 1, 1, 1/2, and 2, 1/4. This is the graph of the exponential function with a base less than 1. So what do we notice? When the base is greater than 1, the exponential function is increasing. When the base is less than 1, the exponential function is decreasing. Is this 1 to 1? Good. Give me an ordered pair so I can graph the inverse. 4 and -2. Perfect.
-1, 2.
2, -1. Right. 2, -1. Then, perfect. So 1/2 1. So 1/2 1. Where they intersect, they must be the same, and that's where the y equals x should go as well. Can anyone give us the domain of this function? Of 1/2 to the x? So 1/2 to the x is defined on all real numbers and range. Very good. So the inverse of that, 0 to infinity, -infinity to infinity. Yes, you're perfectly correct. This function, the exponential function, has a horizontal asymptote. Obviously, the inverse function will have a vertical asymptote, as we know from tangent and its inverse. Tangent had vertical asymptotes. Its inverse has horizontal asymptotes. Same thing here. Okay. Good. Now I would like to graph this function. F of x equals 2 raised to x plus 1 minus 3. I would like you to give me the transformations in the order of operations, and let's use transformations to graph. And then I'd like to look at a word problem. So the base function is 2 raised to the x. Very good. So I know the base is greater than 1. The function has to look like this, and it has to cross at 0, 1. So this is 2 to the x. That's my first step. Step number 2. What transformation is next here? Yes. 2 raised to x plus 1. Where does it go? Exactly. So this point from 0, 1, where will it go? Just this point. Tell me just this point. -1, 1. Very good. Does the horizontal asymptote change? No, because I just shifted the graph to the left. I didn't do this, right? Okay. So the horizontal asymptote does not change. Oops. Good. So this is 2 to x plus 1. Now step number 3 is 2 to x plus 1 minus 3. Exactly. Exactly. We have to shift the horizontal asymptote first. So the horizontal asymptote initially was at y equals 0 for these two functions. Where does it go now? 1, 2, 3. Very good. Y equals negative 3. So now I shift the red graph 3 units down. Give me this point again. Where does it go? Is now at negative 1, 1. Where does it go? Still at negative 1, but down 3. 1, 2, 3. I don't really know exactly where it crosses the x-axis or the y-axis. We'll learn that in this chapter, how to determine that. So for now, I'm just going to graph it like this. So it's 2 to x plus 1 minus 3. What is the range of this function? The domain is already numbers, it's exponential, but what is the range of this function now? Exactly, because it had a downshift of 3. Very good. Okay. I would like to present the compound interest formula, and then we'll look at applications. Compound interest formula. It is an important formula. I don't want you to memorize it. I know it because I'm using it all the time. So A equals P 1 plus R over N raised to NT. It will be given to you in the problem. So what does all this mean? Okay. A is the accumulated value. Just write them right like this right now, and then I'll explain what is everything here and how this works. This is the principal. So this is A, this is P, 1 plus little r, lowercase r, over lowercase n, and everything raised to power n times t. Where A is the accumulated value, P is the principal, R is the annual interest rate, T is time in years, and N is the number of times the interest is compounded per year. Recalculated per year. One more time. A is the accumulated value. P is the principal. R is the annual interest rate. N is the number of times the interest is compounded per year. Recalculated, if you want, per year. And T is time in years.
Did we learn that last?
Yes. Yes. We did. We did. Yes. Because
I forgot what chapter.
it was chapter 12 because we talked about these functions then, but not in so much detail.
Oh.
Yeah. Very good. So let's look at the problem now. On page 309, let's look at problem 54. Compound interest. If $4,000, oh, I need to explain this before we read the problem. Okay, so how does this work? Okay, so let's say I have $1,000 and I deposit the amount at certain interest rate per year. Compounded, the interest is compounded twice a year, let's say. So I'm depositing $1,000 at 5% per year, interest recalculated or compounded twice a year for the next 10 years. This is the amount I get 10 years from now. If on January 1st, 2018, I deposit $1,000 at the 5% for the next 10 years, compounded the interest twice a year, this is the amount I get 10 years from now, the accumulated value. It also works the other way around. Let's say I borrow from you guys $1,000 today, and you lend the money to me at 5%. You're calculating the interest twice a year, and I promise to give it back to you in 10 years. This is the amount that I have to give you back in 10 years. So it goes both ways. Okay? Good. So now in 54 we have $4,000 is borrowed at a rate of, so this is the principal, it's borrowed or invested if it's not borrowed, okay, at an interest rate of 0.0575. We cannot use percentages. It's a decimal. It has to be a decimal number per year. Compounded quarterly. How many quarters are in a year? Okay, so then n equals 4. Find the amount due at the end of the given number of years. So part A, t equals 4 years. Part B, t equals 6 years. And part C, t equals 8 years. So let's put it in the formula and then use the graphing calculator. So I'm going to write A equals P, which is 4,000, in parentheses 1 plus R, 0.0575 divided by 4. And the numerator, the power will be 4 times T. So let's go to the graphing calculator. And in y equals, let's punch in 4,000 in parentheses 1 plus 0.0575 divided by 4. Close the parenthesis. Put the caret. And in parentheses 4 times x. So what do you think I'm going to do next? No, I have x. It's either 40, exactly, just look at the table. Because I don't want to repeat that. Is this the only way? No, but I think it's the best way to do it, to understand what we're trying to do. So I have to go back to table set because, as I mentioned, this calculator resets everything. Okay, so I will punch in 4, I will punch in 6, and I will punch in 8. So if we borrow the money we borrow $4,000 at the rate of 5.75% for the next 4 years, how much do we have to give back if we borrow it for 4 years? We have to give back at the end of the 4th year 5,026.20. At the end of the 6th year, we are giving back 5,634.10. And at the end of the 8th year, if we need to borrow it for 8 years, it's 6,315.60. Need help? So that is the best way to create the function instead of repeating the same calculation in your calculator. It's the best way. Put the function in, you have it, and you punch in the numbers. Is that clear? Is that clear how we created the function? Okay. Okay, I would like to look at 56 as well. And then we can move on. 56. Okay, let me see where I'm with the time here. Oh, okay. Find the present value of $100,000. If interest is paid at the rate of 8%, we cannot use 8%. We have to write it as a decimal point, decimal number. Compounded monthly. How many months are in a year? Okay, and t equals 5 years. So let's talk about this for a moment. Very interesting. The present value of a sum of money is the amount that must be invested now. So I don't know the principal. I don't know how much I should invest now, but I want 5 years later to have $100,000. Exactly. No. So the present value of 100,000. So in the future, the accumulated value is 100,000. But I don't know how much I should invest today to in 5 years to get 100,000. So the accumulated value this time is 100,000. Is this clear? The principal is not known. I don't know how much to invest today so that I have $100,000 in 5 years from now. And what will you put in parentheses? 1 plus 0.08 over, yes, and raised to 12 times 5. This is a simple situation. All I have to do is divide by this number. Don't bother calculating it. Just divide 100,000 by all this. 1 plus 0.08 over 12 raised to power 60. 12 times 5. So let's put it in the graphing calculator. So 100,000 divided by, in parentheses, 1 plus 0.08 divided by 12, close the parenthesis, caret 60, and press enter. So how much should we invest today at 8% compounded monthly for 5 years in order to, in 5 years from now, to go to the bank and say, give me 100,000? 67,121.04. So then the principal is 67,121.04. Any questions? Chris, you want me to go back?
Yeah.
Any questions? Okay. Moving on. Ready? Yes?
Yeah.
Okay. So this was section 4.1. Let's move on to 4.2. Nothing really new in 4.2. You'll see in a moment. It's another exponential function, two other exponential functions. So in 4.2, we will talk about two special exponential functions. In the first section, we discussed that the base can be anything between 0 and 1, not 0, not 1, and not negative, and could be between 1 and infinity. Now we're going to focus on two very important exponential functions. What exponential functions? Here they are. In blue, what does this say? No, in blue. Yes, that's the first one, 10 to the x, and what is the other one? Exactly. These are two very special exponential functions. So 10 to the x and e to the x. As you see, they're so important, and there is a button on the graphing calculator specifically for those two. Separate, right? So 10 to the x is called common exponential function. The other one is called natural. E to the x has a lot of applications. Yes, we're going to get to that. Okay, so now what do we know about number e? Is number e a number greater than 1 or less than 1? Great, it's 2.7. Let's see, it's right here. If you ever forget, it's right here. See the division symbol in E, plain E. So second and division symbol, and press enter. And you have it at your fingertip. That's E. It's a number greater than 1. So coming back, so how will these two functions look like? Increasing on all its domain or their domain, or decreasing? Right, because the base is greater than 1. Perfect. Now, which one of those two will be closer to the y-axis? So both of them will have the same shape, but which one will be closer to the y-axis versus this one? The higher the base, the bigger the number, right? So let's graph both. So we remember that. So e to the x is right here, blue e to the x, and just put x. So the first one in blue will be e to the x. 10 raised to x, no, I didn't mean that. Raised to x. Okay, 10 raised to x would be in red. Ready? Here is blue, and here's x. 10 to the x, coming up. Has to cross at 0, 1. Closer to the y-axis, because the higher the base, the bigger the number. That's why it's closer to the y-axis. Okay? Perfect. So, now, if the interest is compounded continuously, if interest is compounded continuously, then the formula for the accumulated value is the principal and our e raised to rt. There is no n because it's compounded continuously. And now let's look at a problem here.
You got to remember this formula?
No, I'm going to give these to you. So, of course, the same significance. A is the same, the accumulated value. P is the principal. E is the E, Euler's number. A mathematician who bears its name, right? Euler. So E. Very good question. Very good question. One explanation is he looked at limits, which we don't know yet. We will in the next course. So he calculated certain limits of functions, and he came up with this E all the time.
So every time it's like 2 points.
Exactly. That's exactly the same idea as they came up with pi. So here's how they came up with pi. They they determined circles. Okay, so imagine that this is a circle. So they measured the circumference of a circle. They measured the radius of the circle from the center to any point on the circle. It was always the same number. The ratio was for any circle, the circumference divided by 2 times the radius. They came up with the same number all the time for any circle, any small, big circle. For this circle, the ratio between the circumference and the diameter is pi. For this circle, the ratio between the circumference and the radius and the diameter is pi. So that's why they gave it the name pi. Every time you divide the circumference by the diameter of any circle, small or big, you will always get 3.14 blah, 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 blah. The same way he came up with E.
Is E like the same E from E equals MC squared? Or that different?
E equals?
MC squared? The one that...
Yes. No, that's the energy. That's the uppercase E.
Oh, okay.
That's the uppercase E. That's the uppercase E. That's a different thing. That's a formula. Very good. Okay? So that's how pi was determined. They didn't know anything about this. But because it came so frequently and all the time in ratio of the circle divided by the diameter, then they said, okay, this is so interesting, and we're going to give it a name so we don't have to bother with all those decimals. So that's how they call it. They call it pi. Yep. Okay, so of course P is the principal, R is the annual interest rate, and T is time in years. So let's take a look at the following formula. So We have never really had so far so many applications. So look, medical drugs, an exponential function. So what did they do? They collected the information and they plotted points. Well, only this exponential function fits through those points. No rational function, no radical, no polynomial. This function, that's how they came up with it. Okay, then radioactive decay. Radioactive substances decrease their mass in time, so that's another function, mass. That's another function. Skydiving. Look, they came up with this function for skydiving. Mixtures and concentrations. That's another exponential function. Yes, with some transformations in it, not plain exponential function, but it's an exponential function. So all these are on page 313. We can look at anything you want. The tree diameter. They calculate the tree diameter with an exponential function in it. Page 314, page pi. Page pi. Page pi, problem 28. Yes, look at the bird population. Look at the wart population. Look at logistic growth models. All of them have exponential functions in them. So this is, and all of them have the same base, e. So that's why it's called a natural exponential function. It appears in everywhere in nature. From determining the tree, the diameter of a tree, to logistic growth, bird population, world population, skydiving, radioactive decay. It's so widely spread. That's why it's called natural. It's coming in nature all the time, in everything. Okay, so please choose a problem. I hope I convinced you now.
I'm like in third population.
Okay, bird population. Which problem?
26.
26. Very good. So let's take a look at 26. Don't forget, I want to do at least one problem with this formula so you see how it works. The population of a certain species of bird is limited by the type of habitat required for nesting. The population behaves according to the logistic growth model. So this one, again, is so important. I'm not going to ask you to remember the name, but it's very widely used in exponential, in bird populations and others. Okay, so n of t, number of birds, function of time, equals 5,600 over 0.5 plus 27.5 times e, still in the denominator, raised to negative 0.044 t, where t is measured in years. So t, years. Find the initial bird population. So question A, initial bird population. How do I find the initial? When I say initial, exactly. I need to find n of 0. So let's see. Yes, we can put in the calculator, but for 0, it's not going to be a problem. So so negative 0.044 t, 44 times 0. How much is this?
0.
How much is e raised to 0? Excellent. How much is 1 times 27.5? How much is 27.5 plus 0.5? 28. How much is 56 over 28? 2. 56 over 28. 2. So it's 200 birds. Yes, you can put in the graphing calculator if you want. Part B. Draw a graph of the function n of t. We will in a minute. We have to use a calculator for that. What size does the population approach as time goes on? So now if I, for example, I want to add another question here. If I ask you find n of 3, what am I asking you for, basically?
How many birds are made in 3 years?
Exactly. And what if I ask you how much is n of 10? That part we cannot do by hand. The 3 and the 10 we cannot. We could do 0. but not 3 and 10. So let's put it in the graphing calculator because we have to eventually graph it. So in y equals, be very careful how you punch it in. So in y equals, clear whatever you have. And then 5,600 divided by, in parentheses please, 0.5 plus 27.5 times e, in parentheses please, negative 0.044x, close the parenthesis for the power, and then come down and close the parenthesis for the denominator. Be very careful, we need 2 sets of parentheses. So parentheses for the exponent of e and parentheses for the denominator.
Are we putting this x supposed to be 3?
Say it again?
Is x supposed to be 3?
No, because we want to have the function to punch in whatever we want.
Oh,
So it's in y equals.
this is why.
Yeah, that's why we put it. We wanted to create the function and have it there for other things. Do we all have this? Okay, so now we go to second and table. And we want to plug in 0 just to double check our work. Is that correct? We want to punch in 3. We want to punch in 10. And now it says in part C, we're going to graph it in a minute, but it says in part C, what size does the population approach as time goes on? What does that mean? Say it again. Exactly. Excellent. Infinity. Infinity. In other words, as time goes on, there is no infinity, but I'm going to have to jump. Let's see. Let's see what happens. Because it says, let's read the problem one more time. The population of a certain species of bird is limited by the type of habitat required for nesting. So it's not going to blow up because it's limited. Okay? The population behaves according to the logistic growth model. Okay. So now approaching infinity, I'm going to say in 20 years. Then I'm going to say in 4,000 years. Then I'm going to say in 5,000, 50,000 years. Okay.
The number just too big, or stop.
It can be. So I think I messed up something here.
I mean that too.
5,600 divided by, I'll tell you in a minute why. 0.5 plus 27.5. 56. Okay, let me go again. Because it's not possible. What is the, let's take a look, and we'll figure out in a minute. So why am I saying it's not possible? Let's analyze, let me write the answer just for 3 and 10. 2, 2, 7, and 307. You cannot round up, even if it's 307.5, because we can't have 307.5 birds, right? Okay, so just 307. So let's talk about this for a moment. And then we'll figure out if that's correct. So if t approaches infinity, can you tell me what does this approach? If t approaches infinity, infinity times a negative number will be negative infinity. What about e to negative infinity? E to negative infinity. E to negative infinity is 1 over e to infinity. But e to infinity is 3 to infinity. Humongous. 1 over e to infinity will approach what? 1 over humongous. 0, right. Because imagine you have $1, you want to share it with everybody on the planet. How much will you give to everybody? Almost nothing, correct. So then if this thing approaches 0, then how much is 0 times 27.5? 0. So all this goes away. And now I see, I had to divide by 0.5. It's correct. Everything is correct. So 5,600 divided by 0.5. How much is that? Well, it's 5,600 times 2. And that's exactly what we're getting. So now no matter what I do, it will never go above 11,200. That's the limiting size of the population. What does that mean?
This is the only amount.
Right, but what does that mean for the function if it approaches that number and does not go horizontal? Asymptote 11,200. I forgot about this 0.5. I thought it was 1. In my mind, I had 1. That's why I said, how can it go over 5,600? It does because it's 0.5. Okay, so if you want to write 80,000 years, what will the answer be?
11,000.
Exactly, it cannot go beyond that. No matter how much, because that is the horizontal asymptote of this function. So now, knowing that, I am able to graph the function. So let's graph it. Let's go to the viewing window. Oh, first of all, I have to put in a second function. What is the second function that I have to put in?
That was the right.
11,200. Good. So now the viewing window. I don't care for a negative number for x. I will just put 50 years for now with a scale of 10. I don't care for y minimum to be below 0 because we're talking about the population. And y maximum. What do you think about y maximum? At least. Exactly. So I'm going to put 11,500 with a scale of 2,000. And now I can graph. Okay. Here comes the horizontal asymptote. So this was just 50 years. I'm going to change the maximum x to 200 years. See what happens. Much better. Here it is. This is the graph. And here comes the horizontal asymptote. Is that clear? If you change the x to 500 years with a scale of 100. Let's see what happens. Here is the exponential, the logistic growth model, and here comes the horizontal asymptote. Very good. Questions? Questions? I'd like to continue, but if you want to look at another word problem, we can. It's up to you. You decide. Yes. So let's look at another word problem. So let's choose whatever you want. Oh, yeah. Let's also look at, say it again.
Bird problem?
Bird, mixture and concentration, radioactive decay, compound interest. Okay, 32. If 3,500 is invested at an interest rate of 0.0625 per year, compounded continuously, find the value of the investment after the given number of years. Okay, so 3 years, 6 years, and 9 years. So here's the formula. A equals 3,500 times E to 0.0625 T. So it's A of T now. So let's punch it in the graphing calculator as a function. That's the elegant way, and that's the best way. I normally don't say it's the best, but this time I will say this is the best. So in y equals, clear whatever you have. And let's put in 3,500 multiplied by E in parentheses, 0.0625 times x. Ready? So now with second and table, I'm going to punch in 3, 6, and 9. 3, 6, and 9. So we will get, in 3 years, 4,221.80. So A of 3, 4221.80. A of 6, 5092.50. And A of 9, 6142.70. Any questions? Any questions? Any questions? Okay, very good. 4.3. So we talked about, in 2 sections, we talked about the exponential function. Now we are ready to talk about its inverse. We saw the inverse in both situations. We just didn't name it, though. We even graphed it. We even know its domain, right? We know its domain, we know its range. We know how to graph it, but we don't know what it is yet. So here's the graph. This is the graph of the inverse function of 4 to the x. So this is the logarithmic function that is the inverse of this function. So this is a log function. Here, this is the exponential function with a base less than 1. This is its inverse, defined on 0 to infinity. So this will be the log function, log, log function, which is the inverse of this, of the exponential. Both functions have to have the same base with the exponential. If this one is exponential with base 4, this one will be log with base 4. Otherwise, I will not be able to reverse them. It's not going to work. So if this one has base 1/2, this log will have base 1/2. Otherwise, they will not be inverses of each other. It's like, for example, when I say the square root of x and x squared are inverses of each other. Not the square root of x and x cubed. Right? So they have to have the same base. How do we write this function? Here's how we write it. This is f of x, log, same base, lowercase a, the same base we had for the exponential of x. So one more time, how do we read this? Log base a of x. Log base a of x. The same properties for a. A can be greater than 1 or between 0 and 1. If we had allowed base of 0, 1, or a negative, we would have never been able to define this function. That's why we removed that possibility for the exponential. So the base cannot be 0, 1, or negative. In the exponential, and it cannot be 0, 1, or negative in the log. So now we know 2 graphs. This is log base a of x with a greater than 1 because it's increasing. We just graphed it. And we have the other one that looks like this. Still log base a of x, but it does not have a base greater than 1, but it has a base between.
0.
That's it. The domain of this function is 0 to infinity, and the range is everything. So this is a function with problems. Yes, we have 2 special ones. What 2 special ones am I talking about? Natural log and common log. So log base 10 of x and log base e of x. However, we are not going to use any of these 2 notations though. So this is, again, common log. where we don't use this notation. We use this notation. But this is what it means. So if you see a log with no base, it's common log. Now, obviously, this is natural log. But this is not the notation we're going to use. But we're going to use lnx. So important. Let's go back to the graphing calculator for a moment. See, they are on the same keys. log and 10 to x. Use the same key. And e to the x and ln, they use the same key. They are inverses of each other, and they're on the same key. ln is the inverse of e to the x, and log is the inverse of 10 to the x.
So these are the inverses?
The inverses, exactly. We graphed them when we graphed the exponential. Okay, so I know I only have 2 minutes left. So I like to explain the most important concept in this chapter. Okay. The most important concept in this chapter. I consider it. It's the most important in this chapter. In words first, any log equation can be replaced or written, if you want, replaced by an exponential equation, comma, and vice versa. Any log equation can be replaced by an exponential one, and any exponential equation can be replaced by a log. So, here's a log equation. Log base a of x is y. This is a log equation. This is a symbol that is called the double equivalency symbol. What does that mean? If I read from right, I can get to the left. If I read from the left, I can get to the right. It goes both ways. So this will be an exponential equation. So here's how we write the exponential equation. The base, so we go counterclockwise. The base raised to y equals x. The base raised to y equals x. This is the most important concept in this chapter. There are others, very important, but this is what I think is the most important one. Okay, so if I, for example, if I'm given log base 2 of 8 is 3, how will I change this into an exponential equation? Is that true? Good. Here's one more and I'll stop. Log base 3 of 1 is, what do you think? So that 3 raised to some power is 1. What should I have here? Exactly, 0, right? That's it. So let's just see what is left from